Добрый день, давайте начинать лекцию. Надеюсь, что все меня слышат. Okay, let's start the lecture. In the last class, we have considered two explicit codes, namely the Hamming code which is the binary code with the following parameters. The block length is 2 to the m minus 1, where m is an arbitrary integer parameter. Their dimension is m bitless, and the number of the minimum distance is 3, and this is the binary code. And the second family of codes is called the Reed-Solomon codes. Each code in this family is defined by 3 parameters: the cardinality of alphabet q, which should be a power of prime, the block length, which is at most the cardinality of the alphabet, the dimension, and the distance is n minus k plus 1. So both codes are perfect in the sense that the parameters can't be improved, but on the other hand, each of them has certain minor points. The Hamming code is bad because the distance is very small, so it corrects only one error. The Reed-Solomon codes are bad because the alphabet should be large. The alphabet is at least the code block length. So we need to construct somehow codes where the alphabet is small, but still they have decent parameters, namely the decent whose rate is not very low and the relative distance is also not very low. Recall the diagram on which we represent the parameters of the code. We have the sufficient condition, which is called the Warshamov-Gilbert or just Gilbert bound, which says that there is a code below that line, which in the coordinates d over n and k over n and we want to have some code, say, close to this bound, a little bit below, with efficient encoding and decoding procedure. Recall that on that curve, we have codes, but they were constructed using a greedy algorithm. So they can't be used in practice because if block length is large enough, then the set of all code words, first of all, is hard to find. But even if we have found them already, there could be no efficient one-to-one correspondence between messages and code words. So even the encoding might be non-efficient. So somehow we need to find codes with good ratio, with good rate and relative distance, which have efficient encoding and decoding procedure. First of all, we will consider the so-called random linear codes. For random linear codes, the encoding is efficient, but the decoding is not. And they are very easy to construct. What does it mean, a random linear code? First of all, to specify such a code, we choose Q, which is a power of prime, So we will consider symbols as elements of the finite field FQ. So we fix the field. And then we choose the block length n and k, the dimension and the distance, so that those parameters are close to the Varlamov-Gilbert bound. Not exactly on the line, but strictly below the line, so to say here. And to construct such a code, we just choose its basis E1, E2 at random. So assume that we take k elements in the linear space of dimension n over FQ at random independently. So we choose them at random each E sub I is chosen with uniform probability distribution at random uniformly. And independently. So each EI is independent on the rest of the E's. Then we claim that with high probability, the resulting code will have the distance which is close to the, so that the parameters of the code are close to the Varlamov-Gilbert bound. More precisely, we have the following theorem. So assume that our parameters satisfy the following inequality. So q to the k minus 1 times the volume of the ball of radius d minus 1 is less than q to the n times some small number, call it epsilon. So epsilon is some real number in the segment 0, 1. Then this probability close to 1, namely larger than 1 minus epsilon, the random linear code has the parameters, the distance, the minimum distance of the random linear code is at least d. So we assume that mm, we, we assume the same inequality as in the Gilbert bound, but a little bit stronger. So in the Gilbert bound, in the right-hand side of the inequality, we have q to the n. Now we assume that the inequality holds is in stronger form. It is less than q to the n times some epsilon. The less epsilon is, the larger will be the probability that the distance is at least d. Так, скажите, пожалуйста, понятна формулировка?
То есть эта вероятность возникает из-за того, что мы выбрали рандомно базис, да?
Ну, да, мы выбрали случайным образом базис линейного пространства. Да, я, наверное, забыл сказать. Сам код состоит из всех, ну, кодовые слова – это линейная комбинация вот этих базисных векторов. Значит, утверждается, что с вероятностью близкой к единице это не просто линейно независимые вектора, но более того, что расстояние между различными словами кодовыми будет не меньше d. So the set of code words C consists of all the linear combinations of those vectors chosen at random, where the coefficients are chosen in the field, in our field. Ну хорошо, окей. Let's start. Let's start the proof. We know that for linear codes, we can measure the distance between code words in the point zero. That means that the minimum distance of C is at least D if and only if for all non-trivial combinations, non-trivial, that means that at least one lambda I is non-zero. The Hamming weight, that is the number of ones in the corresponding linear combination, is at least D. So we need just to upper bound the probability that this doesn't hold. So the probability that there is a non-trivial linear combination of Hamming weight less than d, that is at most d minus 1. So this where E1, Ek are chosen at random. So this event, whose probability we want to upper bound, is the union of events which are obtained from this event by fixing lambdas, all the lambdas. So using the union bound, we can say that this probability is at most the sum over all lambda 1, lambda k, non-trivial, the probability of event that a particular linear combination has Hamming weight at most d minus 1. To compute this probability, we need to understand what is the distribution of such a sum, lambda 1 A1 E1 plus lambda k Ek, where we assume that all EIs are chosen with uniform distribution. So EIs are chosen in FQ to the N with uniform distribution, and they are independent. If the combination is trivial, that means that all lambdas are 0, then of course this is always 0. Whatever EIs we choose, it is 0. But otherwise, if at least one lambda is different from 0, then it has the uniform distribution. For example, if we have only one term in this sum, say lambda lambda 1 E1, then because of E1 is chosen with uniform distribution, lambda 1 times E1 has also uniform distribution. Another example, assume that we have two terms in this sum and all the remaining terms are 0 because lambdas are 0. Then whatever E1 we fix, this vector has a uniform distribution because lambda 2 times E2 has uniform distribution, and we just shift it by a fixed vector. So if E1 is fixed, then this here has uniform distribution. And this implies that whatever distribution of this term we have, the result is uniformly distributed. And so on. We know that in our sum, at least one term, one lambda is non-zero. Then for every fixed remaining terms, this sum has uniform distribution because of this non-trivial term, and hence it is uniformly distributed. This implies that we can compute this probability. This probability means that this vector, which is chosen uniformly, belongs to the ball centered at 0 with radius d minus 1. So we just need to calculate the volume of this ball and divide by q to the n. So we obtain here the sum over all lambdas, non-trivial, of the volume of our ball of radius d minus 1 over q to the n. And now, so this probability doesn't depend on lambdas, and we have here the sum of constants, which, so the whole sum is equal to the number of non-trivial combinations, which is q to the k minus 1, because the total number of combinations is q to the k. Each lambda I may be chosen in q ways, and we have independently to choose k of them, minus 1 trivial combination. So we have q to the k minus 1 times the volume of the ball over q to the n. And our assumption states that this sum is strictly less than epsilon times q, than epsilon. And so the probability of bad event, that some non-trivial combination has small Hamming weight, is at most epsilon. So this is equivalent that the minimum distance of our code is less than d. So that this completes the proof. Так, есть ли вопросы по доказательству? Что у меня такое впечатление, что все просто спят. Ну, откликнитесь кто.
Мы не спим.
Ну, понятно доказательство?
Ну, вроде да.
Вопрос.
Okay, good. So the first way to construct a code is just to choose the basis in the set of code words at random. With high probability we obtain a code with good parameters. Once we have chosen E1 and EK, we obtain an efficient procedure to encode, because each message is just encoded. So the message corresponds to lambda 1, lambda k. And the encoding is just computing this sum. So the encoding procedure algorithm applied to the k symbol message just output the corresponding linear combination. However, there is no easy way to decode such a code from errors. So in practice, we can't use such a random linear code. But still, this is an interesting thing, and they are used in theory at least. Now let's ask how many bits we need to find such a code. So to find such a code, we need to choose k vectors, and to choose each vector, we need binary log of q to the n bits, which is actually we need to take the integer part of that. Approximately this is kn log q bits to find these vectors. And actually, random bits are a very expensive resource in practice. because the algorithm can't just toss the coin, and we need somehow to simulate coin tossings instead of genuine coin tossings. Usually we use pseudo-random generators and so on. So is it possible to reduce the number of bits? And an interesting idea is due to the scientist called Wozencraft, who designed random codes, but which need much less random bits. And later these codes were used to find efficient codes with other parameters. So now I will explain the simplest example of Wozencraft codes. So the rate of those codes will be 1/2, so which means that the block length will be equal to 2 times dimension. And the distance will be the same as for codes on the Gilbert bound, or more or less the same as for random linear codes. And the alphabet will be binary. This is important. But actually, we can construct such a code also for non-binary alphabet. But let's stick for now for binary alphabet. So what are those codes? The idea is the following. Consider the field of 2 to the n elements. 2 to the n is a power of prime because 2 is prime. So there is certainly such a field, and actually there is a unique such field. And this field may be considered as the linear space of dimension n over the 2 elements field. So to obtain such an isomorphism, we just need to fix the basis. So to choose some n different elements of that field, which are linearly independent over F2. And once we have chosen them, we can consider our field as linear space. Actually, we do not need even to choose the basis but to design a code later, we will need a basis. So anyway, now fix some element, call it alpha, in that field. To each such alpha, we assign a code which is designed as follows. So the messages, oh, sorry, I have confused k and n here. Instead of n, we need to consider here k. And here, sorry. So messages are elements of F2 to the k. So messages are k-bit sequences, which are considered as elements of F2 to the k, and we will use the isomorphism between F2 to the q and F and the field of 2 to the q elements. So here we need to choose a basis, because if we have a message, we have just k bits. And to understand to which element of the field corresponds these k-bit strings, we need to fix a basis. So anyway, given a message, we first find the corresponding elements, and the encoding of this message is the message itself concatenated with alpha times the message. So here we consider the message as an element of that field. We multiply it by alpha, which is also an element of that field. And again, we use our isomorphism to find which k-bit sequence corresponds to that element of the field. So this is the encoding of our message. So all the code words of that code consists of all 2 times k bit strings of that form: x alpha x, where x is an arbitrary k-bit sequence. And certainly this is a linear code. Linear means linear over F2. So because our code is a binary code. So if we have 2 code words, x alpha x and y alpha y, then the sum of those 2 code words is again a code word which corresponds to x plus y, comma, alpha times x plus y. And this is because their addition and multiplication in the field satisfy the distributive law. Okay, now what can we say about the parameters of this code? So the messages have k bits, so the dimension is k. The block length is 2 times larger, 2 times k. The only thing we need to understand what is the distance of that code, the minimal distance. The minimal distance depends on the choice of alpha. Say, if alpha, example, if alpha is 0, then the distance is very low. So the distance is only 2, because even 1, sorry. 2 different code words can differ in only 1 bit, because the second part is trivial, it is 0. So the code is very bad. Actually, each word is encoded by itself. So this is very bad. If alpha say is 1, then we obtain also a very bad code, because this means that we just copy the code word. So the distance becomes 2. So if we have 2 different code words, they may differ in only 2 positions. But it turns out that for the majority of alphas, the distance of the code is very large. The same, so large that the parameters of the code lie on the Gilbert bound. More precisely, we have the following theorem. assume that q to the k times the volume of the ball radius d minus 1 is at most epsilon times q to the n. So we have more almost the same assumption as for linear codes. So we have the same inequality as for Varlamov, Gilbert, or just Gilbert bound, but in a stronger form with epsilon q to the n in the right hand side, where epsilon is a real number from 0 to 1. Then with probability larger than 1 minus epsilon, even strictly larger, despite the fact that we have here non-strict inequality, we can claim that probability is strictly larger than 1 minus epsilon. The minimum distance of C alpha let's see whether I had introduced C alpha. So call it C alpha. So the set of code words of the Wozencraft code. The minimum distance of C alpha is at least D. So we obtain almost the same property, almost the same theorem, but what is the gain? One gain is to specify such a code, we just need to choose k log q bits. Instead of kn log q bits, we have k log q bits. We have reduced n times the number of bits. And also, intuitively speaking, the Wozencraft code is much more effective than the random codes, because we need just, the code is just specified by one k-bit sequence. Log q in our case is 2, because q is 2. Okay. Now we need to prove. First of all, it is worth to rewrite the assumption using the fact that n is 2q, 2 times q. So our assumption actually means we assume that Vq, the volume of the ball, is at most epsilon times q to the k, because n is equal to 2k, so we can cross out 1 q to the k, the factor of q to the k, and replace q to the n by q to the k. Then we need to estimate the probability of bad event. So what means a bad event? A bad event is that some code word, there is x, such that some code word x alpha x has bad small Hamming weight, at most q minus 1. And that word is non-zero. But what means that it is non-zero? That actually means that x is non-zero, because if x is non-zero, then certainly this code word is non-zero code word. And if x is 0, then both x and alpha x are 0. So it is a 0 code word. So the probability bad event means that there is non-zero x. Non-zero x. such that the Hamming weight of x alpha x is at most q minus 1. We need to estimate this probability. And to estimate it, so informally, we will use the following fact. If we fix x alpha x, one of the low Hamming weight code words, then alpha may be expressed through that code words. So for every specific x alpha x, there is only one alpha which is prohibited by that code words. So the probability that our alpha is bet is equal to the number of bet x alpha x, which is the volume of the ball, over q to the k, which is by assumption at most epsilon. So if now I will just express this line of reasoning using the formulas. So the probability of this event may be rewritten as follows: the probability that there is x and y, x is non-zero, and y, where y denote alpha x, such that alpha y is equal to alpha x, and the Hamming weight of x, y is at most q minus, sorry, not q minus 1, but d minus 1. At most d minus 1. So this is just a rewriting of our condition. So we choose alpha at random and want to find out what's the probability of this event. Again, we can use the union bound because we have to choose here x and y. So we need to just, we can upper bound this as a sum of all over all x non-zero and y. X is non-zero. And y, such that x concatenated with y has small Hamming weight, at most d minus 1, of probability of event that y is equal to alpha x. So we use the fact that actually only one part of our depends on the choice of alpha, this one. So we need to just sum up the probabilities of the following events, that y is equal to alpha x. But the point is that if y is equal to alpha x, that means that actually alpha is equal to y over x. And for each particular y and x, there is only one such alpha. Here we use that x is different from 0. So this is just equal to the sum over all x and y, such that this holds, of q to the minus k, because alpha is chosen with uniform distribution among q to the k elements. And so we need to find out how many elements, how many pairs of x, y we have. We have that the Hamming weight of x pair x, y is at most d minus 1. Therefore, this sum, there are at most v of d minus 1 and such pairs. But actually, many of them are bad because we need also that x is different from 0. So this sum certainly has less than that number of terms. So this is strictly less than the volume of the ball times q to the minus k, because the number of terms in this sum is strictly less than the volume of the ball. And by assumption, this is at most epsilon. So this is our assumption. So it implies that it's most epsilon. So the probability of the bad events that are the distance of the code is at less than d is less than epsilon, because we have here a strict inequality. So this inequality is strict. So the probability of bad event is strictly less than epsilon. So the proof is finished now. Так, скажите, есть ли вопрос по доказательству?
Нет.
Хорошо, давайте сделаем на 5 минут перерыв. Значит, сейчас 47, 52 минуты продолжим, чтобы вы могли, я тоже отдохнуть.
Можно тогда просто организационный вопрос? У нас была третья домашка?
Он наушники снял.
Ну, это даже не к нему вопрос, просто ко всем.
Вроде
Была
не
третья
было.
домашка?
Вроде не было.
Ну, я не нашел, и вроде никто не нашел.
Ну хорошо, тогда все, окей.
Позвольте пару организационных вопросов задать.
Да.
Таких. Во-первых, правильно ли мы все понимаем, что третьей домашки не было? Что не недопонимание ли это?
Сейчас посмотрим. Да, я забыл дать вам третью домашку. Есть такое. Такая беда.
Окей.
Да,
А
это правильно. Ну, бывает.
Второй вопрос
Да.
состоит в том, ну вот там написано на сайтике, например, что на зачет нужно там 65% баллов. Как соотносятся баллы от тестов и от домашек?
Там они с весом 1/2, 1/2. Там не написано разве?
То есть, окей, примерно понятно, хорошо.
Ну, там просто посчитается доля решенных домашних задач, умножится на 1/2 и добавится доля правильно отвеченных тестовых вопросов, умножена на 1/2. Вот так.
Окей, это делает очень много смысла, все понятно.
Ага.
А можно еще один вопрос, Николай Константинович?
Да.
Вот по прошлому тесту, на прошлой неделе, там была задачка, ну вот дословно, какая размерность кода Рида Соломона с длиной 256, который исправляет 28 ошибок.
Да.
Насколько я понял из ответов, засчитывался ответ 200, я указал ответ 199 или 200. Почему это неправильно?
Так потому что надо было написать 200. А почему вы или написали?
А почему 190? Ну, в смысле, и тот ответ кажется, что подходит. И та размерность дает 28 ошибок.
Там же округление.
Да, там округление. Именно из-за этого и 199 и 200 подходит.
Сейчас, подождите, я забыл. Как было сформулировано задание?
Длина 256 исправляет 28 ошибок. Рид Соломон. Какова размерность?
Ну, так а почему вы не написали, я не знаю, 173? Тоже было бы верно. Он тоже исправляет это самое, 28 ошибок. Как бы в ответе годится любое число меньше 200. Почему именно 199, непонятно.
Ну, кажется, что 28 имелось в виду, что не более 28. Но обычно же мы в этом смысле подразумеваем.
Ну хорошо, я наконец понял, да. Я вам исправлю, да. Я вам поставлю правильный ответ, да. Мне просто надо было точнее формулировать задачу.
Ну да, если была написана
Я
максимальная
имел в виду максимально возможную размерность.
Да, я понял. Если была максимальная, тогда, конечно, было бы 200.
Да.
А так вроде и то, и то.
Да, понятно.
Хорошо, спасибо.
Ладно, давайте продолжать. Okay, so we have seen that there are random linear codes and Wozencraft codes, which are sort of also random linear codes on the Varlamov-Gilbert bound. But still for both family of codes, there is no efficient procedure to decode from errors. So they, again, can't be used in practice. So now we will finally, after all, design such codes, which can be used in practice because they have both efficient encoding and decoding procedure, and they have good parameters. And this is done using the so-called concatenated codes. So let's, I'm sorry, there is no A here, just, there is A, concatenated codes. So recall the Reed-Solomon codes. Why are they bad? They are bad because they have large alphabet. How can we reduce the alphabet? Assume, for example, that we have a Reed-Solomon code whose alphabet is has, say, 2 to the m elements. Say 2 to the m, something, some k, some d. How can we reduce the alphabet? Assume that we are looking for a binary code. Then we can think of each letter of this large alphabet as m bits. And we can just replace in each code word one letter by m bit sequence. So from this code, we may obtain the code which is binary just by replacing each code word by its binary code. For instance, if we have a code word 70, 5, assuming that m is 3, so we consider these digits as elements of the field of 8 element. We replace this code word by a sequence 1, 1, 1. This is a code of 7, 0, 0, 0, 1, 0, 1, and 1. Sorry. 101 is a code of 5 and not of 3. 011 and 101. So instead of 4 symbols, we have 12 symbols. So their code length is multiplied, the block length is multiplied by m. So what happens with the dimension? So if we have the dimension k, that means that we have 2 to the m to the k messages, or 2 to the m to the k code words. This is the same as 2 to the mk. Code words. And so their dimension is also multiplied by m. So because the number of code words expressed as the power of the alphabet is mk now, 2 to the mk. And the distance remains the same because if we have 2 different code words, they differ in at least d symbols, and the binary codes of those d symbols differ in at least 1 position each. So we obtain at least d different symbols in different code words. So in general, if we have here not 2 to the m but arbitrary m, which is at most, of course, 2 to the m if we consider it Solomon code. Then we multiply, we obtain here also k times n times n times m. So what can we say about this transformation? So the rate remains the same. So we have the rate k over n, and the new rate is km over nm, which is the same as the previous, the initial rate. But the relative distance becomes much less because we had initially d over n as a relative distance. And instead of that, we obtain d over n divided by m. So the relative distance becomes m times smaller. That means that if the initial code Reed-Solomon corrects, say, 10% of errors, then this new code, binary code, corrects only 10% over m errors. For large m, this is negligible. So this is a very weak transformation. It decreases the number, the percentage of corrected errors very much. So instead of this trivial transformation, we need something more smart, more ingenious. And this more ingenious procedure is called the concatenation of codes. In Russian, it's called каскадные коды. Но только не пытайтесь, лучше не пишите по-английски cascade codes, поскольку это будет неправильно. Такого слова в английском не используется. Okay, what is concatenated codes? So we need to improve D, so make D better. How this can be done? Instead of encoding each letter of the large alphabet using just its plain binary code, we can use in this place some error correcting code. For example, Hamming code or whatever. So, and such a transformation is called concatenation of codes. So in general, we have two codes, which are called the outer code and the inner code. So the outer code, which in practice are usually Reed-Solomon codes. And let's denote its parameters by, say, N1, K1, and D1, and that's alphabet by Q1. And informally, Q1 is large, and we want to decrease it somehow. And to this end, we use the inner code. Whose parameters are N2, K2, say, and D2. And the alphabet is Q2. And to use the concatenation, we need some relation between these numbers. And the relation is the following one. Each letter of the outer alphabet should be somehow identified with the message of inner code. That means that Q1 must be equal to Q2 to the power of K2. So this is assumption under which we can make this transformation, construct the concatenated code. So we have some outer code, some inner code, and whose parameters satisfy this inequality. Q1 is equal to Q2 to the power of K2. In this manner, we can sorry, not in this manner, somehow we will, to construct a concatenated code, we will fix one-to-one correspondence between the outer alphabet and the sequences of of K2 symbols of the inner alphabet. So each letter of the outer alphabet may be understood as a sequence of letters of the inner alphabet. So from this pair, we can construct, using concatenation, the code which is called the concatenated code. In the following way. So we will compute its parameters later, but one parameter is clear at the very beginning. So the whole idea is to reduce the alphabet. So the alphabet of the concatenated code will be the alphabet of the inner code, which is surely smaller than the outer alphabet of the outer code because of this inequality, assuming, of course, that K2 is large. So K1, Q2 is exponentially, so to say, smaller than Q1. And the idea is the following one. We use the outer code in which each letter is considered as a message of the inner code, and it's encoded by the inner code. So that means that the concatenated code has the following set of code words. Each code word is specified by a code word of the outer code. So assume that some X is a code word C of the outer code. So call its letter by X1, X2, and so on. X n minus, n1, xn1. Then, using this one-to-one correspondence, replace each xi by a word of length K2, call the resulting word by hat x. So replace each xi by K2 symbols of smaller alphabet. So we have, instead of letters, blocks of K2 letters. Each block has K2 letters of the smaller alphabet. The total number of blocks is the same, n1. And now encode each block using the inner code. That means replace it by its code. We then obtain a larger block of n2 symbols. From each block of length K2, we obtain another block of n2 symbols. And the number of blocks remains the same. That is n1. So in this way, we obtain the set of code words of the concatenated code. So that means that C concatenated is equal to all such tilde x obtained from all code words of the outer code. Так, понятно определение?
Да.
Now we need to compute the parameters. First of all, what is the block length? From this picture, it is easily seen that each code word of the concatenated code is the sequence of n1 blocks where each block has length n2. So we obtain n1 times n2 as the block length. Now, what is the dimension? So the dimension is how we compute the dimension. We take the logarithm. So the dimension is the logarithm base q2 to the base q2 of the number of code words. But the number of code words is the same as for the outer code, which means that log base to the base q2 of q1 to the power of k1, because this is the number of code words in the outer code. So how to compute this logarithm? We know that q1, we know this. We know that q1 is q2 to the k2. This implies that that logarithm is equal to k1 times k2. So we see that the dimension is also the product of the dimensions of the initial codes. And somehow it magically happens that the distance is also the product of two distances. So it's very easy to memorize the parameters of the concatenated code. Everything gets multiplied except for the alphabet. So how it happens that the dimension is also d1, d2 times d2. Look at this picture. So assume that we have two different code words x and say y of the outer code. Then the sequence are different, and moreover, there are at least d1 different letters in two code words. That means that here we have at least d1 different blocks into in x, hat x and hat y. But after decoding, encoding using the inner code, each of different blocks produces d2 different symbols. So we had d1 different blocks, and after encoding each pair of different blocks produces d2 different symbols. So in total we obtain d1 times d2 different symbols. So which means that the distance is also d1 times d2. Ну что, понятно это с параметрами?
Да,
Да.
Well, here is an example how we can reduce Так, надо мне новое открыть. Не то, зачем почта? Так, новую сейчас откроем доску. Сейчас я вам скину в чат, чтобы удобнее было. Так, вот ссылка. Мгм. Here an example. Assume that we have, say, 27 13 and 15 read Solomon code over the alphabet of 27 letters. And the inner code should be then have 3 letters. The dimension should be also 3. And for example, we can use again read Solomon code, say of length 3, and oh, this is not interesting. Okay, let's use another code, say instead of 3 here, 2. I think that we have such a code, 2, 3, 2, 3, 2. Okay, and using the concatenation of that code, we obtain a code which has 54, the block length is 54, the dimension is 39, and the distance is 30. And the alphabet has 3 letters only. So we have compared to the initial read Solomon code, both the rate and the relative distance have decreased, but the gain is that now the alphabet is smaller. So what happens in general? We on this picture with the rate and relative distance, we have some code here, and then whose parameters are k1 over n1 and d1 over n1. And this pair of parameters is replaced, both are decreased. K1 over n1 is multiplied by k2 over n2, which is, of course, at most 1. So the rate gets decreased. And the same happens with the relative distance. It is also multiplied by d2 over n2. So we have some pair, some outer pair, some inner pair, say here. And from that we obtain a pair which is below both pairs. So this pair is obtained by the component-wise product of the coordinates of this pair and this pair. So this is concatenated pair. So we lose in both rate and relative distance, but we obtain a good alphabet, a small alphabet. Так, ну ладно. Я чувствую, что пора уже вам тест давать, потому что через 10 минут все надо заканчивать. Поэтому на сегодня больше ничего рассказывать не буду. Сейчас я вам тест найду где-то, дам ссылку. Так. Тест. Вот там ссылка на тест. Решайте, значит, 35 минут финиш. Когда пишете параметры кода, не ставьте там пробелы. Так будет проще проверять.
А их записывать, как вы писали, в
Да, да, точности.
Добрый день, вы получили мой тест?
Сейчас.
Поэтому
Да, получил.
хорошо, до свидания.
До свидания. Так, минута осталась. Так, 10 секунд, 9, 8, 7, 6, 5, 4, 3, 2, все, закончили. Все, всего хорошего, до свидания. Но сегодня я не забуду вам дать домашнее задание.
До свидания.
До свидания.
До свидания.
До свидания.